to forward.
All right, thank you everyone for showing up virtually to our Faces of Physics speaker series. So I definitely want to thank our speaker for donating some of his time this evening for this SBS speaker series. But I also want to thank AJ Messenger. He's done a fantastic job so far presenting the speaker series. We got a couple more speakers that are going to be presenting throughout the end of the semester here as we complete it. So I want to thank AJ. He's again done a great job with the speaker series. So I also want to thank the physics department, the College of Science, Marshall University, American Institute of Physics, and the West Virginia Space Grant Consortium. Throughout the years that we've done this so far, they've contributed and sponsored the series. So I want to take the time to thank them for that over the years. Currently, for this calendar year, it is sponsored by the SPS Physics Society of Physics Fund. That's an endowed fund set up by an external donor, as well as the West Virginia Space Grant Consortium. They are paying for the 2023 calendar year for this speaker series. So Marshall University has about 9,000 undergrad students and about 2,500 grad students. So if you're interested in the field of physics, look us up. We are currently around a 6-person department. We have 4 faculty that are tenured and active in research. You can look us up at www.marshall.edu/physics. AJ here is our acting interim president for our Society of Physics students. It's an award-winning student organization. So we'd like to do a lot of outreach with the public. So if you're interested in what you hear tonight, definitely contact our speaker at WVU and talk with him. If you're interested in some of the research that happens here at Marshall, also give us a call, talk to somebody. We'll make sure that we get your questions answered for those research questions as well as academic program questions. For academic programs, we have a BS degree in physics, and we also have a master's degree in physics. So we have a couple different tracks for our bachelor's of science degrees. It's a pure path, applied physics path, a biophysics path, a medical physics path, as well as a new medical imaging track, rather. So you still get a BS degree with those career paths or degree paths, but then in most of those areas of emphasis, you pick up a minor degree as well. So if you're interested in the master's program, please shoot us an email, shoot me an email at mcbride@marshall.edu, and I'll be happy to answer any questions that you might have in those areas. And with that, I think I'm going to turn it over to AJ, and he's going to properly introduce our speaker for tonight.
All right. Thank you, Dr. McBride. And also thank you to everyone that's in the YouTube live right now. Thank you for coming out to this live at 7 p.m. Eastern Standard Time, February 27th. Tonight, we will be hosting Professor Aldo Romero from West Virginia University. I will be introducing him here shortly properly. But first, I want to remind everyone that there will be a Q&A session at the end. It'll be about 15 minutes towards the end. So any questions you may have during Professor Romero's presentation, feel free to share with us in the chat, and we will make sure to get to that at the end. Now it's my pleasure to introduce our speaker, Professor Aldo Romero. He is an Eberly Family Distinguished Professor in Physics at West Virginia University. He obtained his PhD in Physics and Chemistry from the University of California, San Diego. After postdoctoral experience at Max Planck Institute in Germany, Professor Romero was faculty in Latin American countries before joining West Virginia University in 2013. He is a co-author of more than 250 publications in different fields and high-impact journals, mainly on computational material sciences. He is also a fellow of the American Physical Society and a Mexican Academy of Science member. Thank you all for coming out to this talk tonight on YouTube Live, and a huge thanks to Professor Aldo Romero for taking the time to talk about his work amidst his very busy schedule during the spring semester. I will now turn it over to our speaker. So without further ado, Professor Aldo Romero.
Well, thank you so much for the invitation. I'm very excited to share what I have learned in the last few years with you guys. As I was discussing with AJ, I would like to make it as friendly as possible. Therefore, you can, hopefully, I will keep you entertained for the next 40 minutes with something that you're going to be excited about it. everything is going to be related to computational material science, but there is only one equation in the whole talk. And hopefully it's not going to be so complicated. And it will be mostly based on concepts and ideas that we have been dealing for the last few years on how to design materials. And without any further ado, let me share my screen. And AJ, can you confirm me you see my screen? Excellent. Very good. First of all, let me introduce the title because I think that's the most difficult part of the talk. And hopefully with this, I will keep you entertaining for the next 40 minutes. And the question that I'm trying to address during this talk is, can we really design materials from scratch? I think right now, when you talk to any physicist, they will tell you that this is very hard and most of the design should happen in the experiment. And I agree with them, but mostly because we, from the computational side, we are developing the tools, but we have a lot of problems that we have to face. Nowadays, I think the situation is changing. And now computational material science is leading the effort and is working hand by hand with experimentalists to make this happen. Therefore, I hope I will convey the idea during this talk. I will not proceed without the acknowledgement, the support that I have received from the Department of Energy in the Office of Science, and of course, the National Science Foundation and the West Virginia University for supporting my research. Let me give you a small motivation. And I think what you are going to see here is a small movie of a beta tin transformation. And what they do is that they decrease the temperature up to minus 40 Celsius, okay? And what happens is that the volume changes and it breaks the sample. Therefore, this is not so amazing. Well, from the material science perspective, it's so amazing that this transformation happens and what is that transformation is capable of. But I think more important is that this is the reason, or scholars think that that's the reason why Napoleon lost his work against Russia. And the reason for that is because the buttons that they use in their pants, it seems that they were done with tin. And then when they went to Russia and then went into battle, the temperature decreases such that the button breaks, and then they didn't have any way to keep the trousers together. And I think some people claim that that's the case. And there are serious agencies that offer some support about this idea. For the question that we are trying to address is that if we know how materials behave and if we know how they transform, can we predict how they will behave in other environments? And that's one of the questions that I'm trying to address in this talk. And for that, I need to tell you how I'm going to be defining a material. And from the theoretical perspective, the way that we think a material is, first of all, I'm going to assume that the material is a crystal. When I'm saying that it's a crystal is that you have a small piece like a brick and you repeat it all over the place such that you are able to fill out the space, okay? Therefore, I'm going to denote that crystals with the following variables. First of all, I will have atoms. The atoms will correspond to a specific species that you will define what they are going to be in the material that you are going to study. Therefore, those atoms are going to be sitting in specific locations. And those locations, I'm going to denote them with this R bar that you have on top, which represents a vector. And this is going to be the position of every one of the atoms in this specific unit cell that I'm going to be defining. And then I'm going to be defining 3 vectors, and those 3 vectors will correspond to the directions of the unit cell that I have created. And based on these 3 vectors and the atomic positions, I should be able to recover the whole crystal. Because the crystal, the unit cell is like a Lego piece, and the only thing that you have to do is to repeat the Lego piece all over the place until you get the crystal structure that you are looking for. Now, the question is the following. Let's imagine that now you parameterize this crystal with atomic positions R sub I and with the crystal vectors A, B, C, and then you define an energy. Therefore, you will define how the atoms are going to be interacting with respect to each other. Therefore, this energy will be a very complicated function of the atomic positions and the crystal vectors. And if I make a very simple representation of what is that, therefore, this looks like this surface that I'm showing here. Therefore, if you think about that this surface will represent this energy, that means that I will have minima and I will have maxima. And what I'm interested in is in trying to locate what is going to be the minimum. And in particular, the most interesting of all will be the global minimum. Therefore, I need to find numerical methods that allow me to walk over the surface such that I can start from a given minimum until I get to the global minimum. Okay, that's the physical problem that I'm trying to solve. In reality, this is more complicated than that. In reality, what happens is that you can be in a minima, and then this minima can have many small local minima very close by. Therefore, it means that we are in what we call a funnel. But it can, therefore, that will mean that I hope you are able to follow my arrow or my cursor. And what I'm trying to say is that if this small minima happens, then they are connected with respect to each other, but they do not correspond to the global minima. Therefore, the question that we need to address one way or another is how we can go from one minima to another minima. How do we do that? Well, we have to create an algorithm that will allow me to travel over the surface such that I can be in one minima, and then in the next iteration or after a few iterations, you are in a different minima. And if you allow that exploration, then you will be able to locate sooner or later what is going to be the global minima. Just to show you how complicated it is that, let me consider one single atom, and I'm trying to build all possible crystal structure for crystal that contains only silicon in it. Over here, you will see three different bars. One corresponds to the red color, the other ones correspond to the green, and the other one corresponds to the blue. The one that corresponds to the red color corresponds to three-dimensional structures. The one that corresponds to the green color corresponds to two-dimensional structures, and the one in blue corresponds to one-dimensional structures. The one in 3 dimensions is the bulk structure that I was talking about. You have a brick, and you repeat the brick in all 3 directions, and then you will cover the whole crystal structures. The green will correspond only to do that, but in 2-dimensional materials. And the case of the blue will correspond to the 1-dimensional material. What is interesting from this plot is not the fact that we can distinguish them from dimensionality. What is more important is that every one of these components of the bar that you see is a line, and there are a huge density of lines. Therefore, that means that every one of these lines corresponds to a different crystal structure. Therefore, if you think about it, you will realize that only to compute all possible crystal structure of silicon, you will have a humongous number of candidates. And the question is, can we find the one that are experimentally interesting and the one that I can synthesize experimentally? Therefore, you see it, if I go back to the plot that I created before, in which I have an energy surface, every one of those minima that I discussed before will correspond to every one of the lines that I have in this bar, for example, in the red case. But the one that I'm interested are the ones that are very low in energy that will correspond to probably to the lowest energy configuration that I'm looking for. Therefore, in order to make it in a little bit more perspective, let's consider a theoretical view of what is done experimentally. Let's consider that I have 4 guns, and every one of these guns have different species. Okay, and then I will just launch the guns with a specific number of atoms and put them in a box. Therefore, the question is, can we use theoretical methods that we develop in physics based on quantum mechanics and classical mechanics that describe how the atoms are going to see each other, and being able, based on those physical laws, predict what will be the crystal structure or what will be the low energy configuration of this atomic composition that you are interested in. Therefore, at that point, you can select the theoretical method that you want to use. You can use classical mechanics, you can use tie binding, you can use density functional theory, or you can use more complicated methods that people have developed in the last 50 years. Then based on the theory, you are going to be able then to define what will be the search method that you are going to use. And after that, you can just create a machine that take this configuration and search over the over the energy surface that you want to investigate. And if you do it correctly, and this is an actual example of something that we do in our research group, you will find that from all possible combination of the atom that you have in that physical box, at the end of the day, you will find a crystal structure that represents a periodic system that will be replicated over the whole 3-dimensional space that I have. Then if I know the crystal structure, if I know the atomic position, and I know the cell vectors that define the unit cell, therefore I should be able then to do a characterization and study any property that I'm interested in. I can study thermal properties, which are represented by the phonon spectra, or I can study the band structure, will represent most of the electronic properties, or I can study optical properties, which will represent excitations from the occupied state to the unoccupied state, etc. Therefore, using the structure, we will be able to know many of the properties by using theoretical methods that people have developed in the last 50 years. But now let me go back to the problem of interest, which is trying to design materials. And usually what we have is that we have developed methods in different areas. Therefore, I'm going to be discussing very quickly over the most important method that people have been using. The first one, which I've received a lot of attention, especially in the last maybe 5 years, is based on machine learning. And the idea here is that you will be able to obtain a structure that people compute by using very accurate method. Therefore, you know the structure and you know some property, let's say, for example, the energy, or other property like the band gap or the magnetic moment or any physical property of interest. And then the idea here is to use these methods that allow you to correlate what will be the property that you're interested in with respect to the atomic positions. In particular, for example, you will be able to predict the energy of the system if you know the atomic positions. There are many different methods that people have used during the years, between Gaussian processes, deep learning methods, kernel regressions, and so on. The one that I'm going to be presenting, and at least some applications that I'm going to be discussing, are based on neural networks, but it's not the only method that people have been using. I want to be honest about that. Another method that people have been using in order to create this crystal structure is based on a metaheuristic approach. And a metaheuristic approach is a strategy that allows you to search over this energy surface in an efficient way, but non-deterministic. In some sense, what you do is that you try to put many players over your surface and try to locate which of the players that you are moving on your surface have the best course of action in order to detect the lowest energy configuration. There are many different methods that the people have developed in the years, like simulated annealing or genetic algorithms, or the fly-firing method, which is the one that I'm going to be discussing, etc. One thing that we have to keep in mind before we discuss other methodologies is that we have to be aware of what is called the Geiger effect: garbage in, garbage out. The Geiger effect comes from the fact that if you are going to be training, for example, a machine learning based on theoretical calculations, we need to be sure that the theoretical calculations that are fed to the machine learning are accurate enough, and they are very well performed, such that the machine is going to be really learning the correlation based on very good calculations. Therefore, you can find in the literature, for example, people that have done this type of developments, but sometimes they use the wrong theory, or they use maybe the wrong pseudo-potential, or there is something wrong with the calculation that they have done, which is not will not give you the accurate result that are expected. Okay, now to finish with respect to the methodologies, let me discuss two other methods that people have developed. One is based on what we call dynamical search, which is very similar to what was explained at the beginning. Let's say you have this energy surface, and consider that you are trying to detect what will be the minimum. Therefore, a very simple way of thinking about that is that you imagine that you have a ball. Therefore, that will represent like a crystal structure, and you let the ball roll over the energy surface, such that depending on the energy that you pick up and the velocities that this ball will acquire, you will be able to jump over the different minima. Okay. And for example, methods that are based on that idea are the Bayesian hopping, the minimal hopping, and the metadynamics. I will explain you a little bit more about the minimal hopping, because that's the one that we have been working in my research group. And the last method that I'm going to be describing, which I think is one of the oldest methods, is what we call a comprehensive approach, or a comprehensive design. And the idea here is that we know already that this crystal structure that I showed you at the beginning, they have a specific symmetries embedded into the crystal shape that you have. That means that because of that, there are only very few space groups that you can create. There are only specific combinations of atomic position that you can define. In total, for crystal materials in 3 dimensions, you have 230 space groups in total. In the case of layer material, there are only 80. Therefore, you can see that even though there is a jam, we can describe clearly what are going to be the atomic positions and what will be the typical cell parameters that you can use in your search. Therefore, the method here is just to use the fact that for a given combination of atoms, you can define what will be the space group that you're interested in. And based on that, you can select the typical atomic positions for that space group and create the crystal structure based on that. And I will show you some experiments based on that idea later on in the talk. Okay. Now that we have defined the 4 different methods, I will try to show you different applications that we have developed in my research group, but with the main idea not to show you that we are very cool and we are doing very interesting science, but mostly to convince you that this type of methods will provide a real insight into the design of materials. But before doing so, let me show you the theory that we have been using. Therefore, I will show you, without any equations, I will show you the importance of this theory. And for everything that I'm going to show you, we have been using density functional theory, which is a theory that was developed mostly in the chemistry community at the very beginning. Now is everybody's using that in the physics and the chemistry community. Even more, the Nobel Prize that recognized this effort was awarded in 1998 in chemistry, not in physics, which recognized in chemistry the effort that people have done in this theory. But these 2 plots that we compiled for a paper that we published like 2 years ago is just demonstrating, for example, the number of publications that you see as time passes by. And you can see that the growth of the number of papers goes exponentially. Only in 2019, there were 14 publications using density functional theory. Therefore, you can see that nowadays, people use this type of theory to do a lot of things, but basically it's showing that the power of this theory is very good. We get very accurate results depending on the property that you are looking for, of course. The other one is just reflecting the fact that that this is also a theory that instead of having 1,000 authors in a paper, it's a theory where only very few are involved in the work, because it's a theory that we can control very well, and we don't need 1,000 hands to develop the method that I'm going to be describing later on in class, in the talk. Good. Now that we have the theory, therefore we have to build things on top of that. And for that, we have created a large series of packages that allow me to control the use of this method and how we can use the material design part. Therefore, for that, everything that we have done is based on Python. And we have created a lot of interfaces that are able to do methodistic method, that are able to run a dynamical method, or they are able to use any one of the methods that I described before, even the machine learning side. Everything is stored in very well-known databases that people developed in Python. Everything is very well connected, and the interface is hopefully is becoming more useful for the community nowadays. For the DFT side, for the method that have been created to compute the energy, we have created specific interfaces to different packages that people developed during the years. I think the most important in my research group is called Abinit, because we're core developers of this package. But also we have created interfaces with other packages like DFTP Plus or Octopus or VAS, which is maybe the DFT package more used in the community more than any other packages. And I don't want to enter into the reason, but I think it's a very interesting philosophy what they keep in this package. We also have an interface with Siesta, which is a Spanish development package, and it's a very good package, especially when you are scaling with respect to the number of atoms. And also we have an interface with Maze, which is a machine learning potential that is created based on neural networks. We create all the different interfaces that allow you to launch a calculation, check the calculation, revise that the calculations are converging correctly, and all of that. Therefore, we are trying to take the heavy weight from the user and trying to allow the user to focus mostly on the physics and not into the details on how the calculation is created. And last thing that I want to just point out is that we also create packages that allow us to do the electronic structural analysis. And this package is something that we published several years ago, even though the first paper came out 2 years ago, which is called PyProCar. And PyProCar allows you to do a lot of analysis on the electronic structure, therefore meaning that we can obtain the electronic properties of a given material with a lot of detail. Therefore, we can understand how and why the electronic properties changes because of several reasons that you have done into the material that you are trying to study. Okay? And this particular plot, for example, the one that you have on the right, for those ones that don't know a little bit of physics, corresponds to the Fermi surface of a topological material in which the topological material happens to be with a magnetic vector. that represent the different interactions in the material. Okay, for now, let me go over the different methods that I described before, and I will go very quickly on how this method works. I will try to get it as simple as possible, but conveying the main idea behind the method. For how this method of machine learning came in, well, they have been used in the community, especially in the STEM sciences for the last, even though they were created in the 60s, the whole development started in the 60s. The big push happens when the big computers came in and when a lot of new databases came in available for the community in general, for people doing image analysis and things like that. In the case of material science, what we have been able to do, especially in the last maybe 10 years, is that we are able to translate the language of bonding and coordination and atomic positions into a set of vectors which correspond to fingerprints. How we do it? Well, there are different methods. Now, maybe the most used method is based on what we call graph neural networks. I'm not going to be describing that, but the basic idea is that we use the connectivity of the different atoms, and we use the angles between the different atoms, and we use the species type that are present in the material that you are trying to study, and you can capture that in a way that you collapse all that information in a single vector. And then based on that single vector, we can compare, and we can use or define what we call chemical distances, which represent that based on the fingerprint that you have created, based on this vector of characteristics that you were able to create, you can represent how the two different materials are similar to each other, okay? And if we have that, then now we can use it for many different applications. For example, we can use it that based on the crystal structure, we can predict properties like the band gap, or properties like the hardness, or properties like many other physical properties that you can measure in experiments. For now, you can see the useful of this. Instead of now using density functional theory to do the whole process, instead, what we are going to do is we are going to start with this representation of the crystal in these fingerprint vectors, and then we are going to train the machine learning to predict the property that we are interested in. And if we do a good job on that, then we should be able now to receive a new crystal structure and then being able to predict the property without doing a single DFT calculation. And that's very exciting. Of course, the risk that we always have is that we never know 100% for sure that we have done a good job. Therefore, we have to be aware that error needs to be classified, and we need to understand how those errors have an impact into the prediction that you are trying to make. And there are methods that you can do so. Just to show you two different examples, this application comes from this paper published very long ago in Scientific Reports. Very long ago means 2013, it's only 10 years ago, but in any case, that in machine learning is already quite a lot. This is just a representation of a property that is predicted by using machine learning with the one that is obtained experimentally. And if the two quantities agree with respect to each other, you have to see a line along the 45 degrees in the plot that I'm showing here. And you can see all the different properties from the dielectric constant to the lattice parameter to the formation energy are very well predicted by this machine learning method that they use in here in this particular application. Therefore, what they demonstrate is that using the crystal structure, you will be able to predict a particular property, and that particular property really capture the environment of the atoms, and that's the most important thing that is captured by these machine learning methods. This is another recent paper that just came out last year, which what they do is that they have a system that they represent through a graph. And this graph captures the different, they capture the neighborhood of every one of the atoms. Therefore, they capture the bonding, and they capture the angles, and they capture the dihedral angles between the different planes that you have in your crystal or your molecule. With that, you will be able to create this feature vector that summarizes the different interactions, but now as a vector of numbers. And then you can use many different machine learning methods. I'm not going to be describing this here, but this is based on a convolutional neural network. And with that, you will be able, for example, to use the prediction of a property. And what they did in this paper was a very beautiful representation that by using this modern method, you will be able to go from a crystal structure to the property in a single step. The beautiful about doing all of this is that now you can see that the first part of the training, where you capture just the topology of the crystal structure, that can be done without the constraint of defining which property you want to predict. Therefore, if you do this process for, let's say, 100,000 materials, then the last part, this multi-layer perceptron, this deep neural network, or this dense neural network, what is also called in the literature, is only the part that needs to be retrained in case that you want to change the property from A to B. Okay, good. Therefore, this is one of the methods people have demonstrated that useful. The other method is metaheuristic algorithms. What I told you is just based on a population. Let's say you have your energy surface, and you are going to be putting a lot of these possible configurations, meaning crystal structures, over your energy surface, and you are trying to see how these guys will walk over the surface and will be able to detect which of the energy minima will be the lower energy. Okay, instead of explaining you the basis of that, or giving you the different type of method that people have proposed, which most of them are based on nature, like the genetic algorithm or the B algorithm or the Wolf algorithm or the Firefly or whatever of the method that people have proposed. Let me show you how it works. Therefore, this is the question. This is the only question that you are going to see, but I'm not going to explain it because I think seeing this visually is easier to understand how these methods work. Therefore, for that, let me consider this very complicated energy surface. And this is a toy model. Therefore, this is not that realistic, but you see that this surface depends on two coordinates. Therefore, you will have your X and Y coordinates, and then the height of that will represent the energy. Okay. And what we would like to find is that based on this, I would like to find where is the place, or what are the values of the X and Y, what are going to be the values of those coordinates that will give me the lowest energy. Which one will be the lowest with the highest height, depending on where you define the height. Okay, in order to do that, what I'm going to do is taking exactly this two-dimensional figure, and I'm going to just to do a two-dimensional representation of that. Therefore, this is what we have in here. And over here, I have the values as a control lines that will represent what is that. Therefore, the next thing that I'm going to do is I'm going to be randomly put a series of structures into this energy surface. And then the first thing that I'm going to do is, based on those structures, I'm going to make the system walk to the closest energy minima that they have. The closest energy minima is not the global minima. It's just a minima that happens to be close to the structure that you have defined. For now, you just let the structure to go down. Therefore, we are going to see that in action, because I will follow that. Therefore, I will do that. The structures go down. And the next thing that I'm going to do is I'm going to say, okay, for every structure, the structure is going to move in the direction of a structure that happens to be in a lowest energy state. Okay. Therefore, for example, if I see the structure that is in 2200, therefore that structure will remain there if this is the global minima. But instead, the structure that went to the 6400, therefore, because this is not the lowest energy, therefore I will change the position of this minima just structure, and it will move in the direction of the 7200. Okay. Therefore, what it basically does is it says you take the structures, you go into the global minima, and after that you will compare the energies of each one of them and say, oh, these guys have very low energy, the other ones have high energy. Therefore, I will try to distort the structures of the ones which are higher in energy, so that they resemble the ones in the low energy, the ones that are in low energy. And in principle, this algorithm should be able to help you to define which is going to be the lowest energy. This is another representation of how the algorithm works. I think I can use the previous image, and I don't want to explain this particular representation because it's happened the same one that I presented before. I will go back into that because if I have time, I'm going to be discussing a few applications that we have done by using that methodology. The other method that I found really, really cool, because from the physics perspective, it tells me a lot about how the energy surface looks like, is the so-called minimal hopping. And the minimal hopping is very simple in the sense that it's based on what we call molecular dynamics. Therefore, what we do is that we take a structure, is randomly found. Therefore, we put the atoms randomly. We create the cell parameters completely random. And what we do is that we minimize the structure, first of all, to the local minima. After that, we have a technique that is able to detect in which direction the structure will distort easier. In the language of people that knows a little bit of physics, they know that the only thing that we need to do is to compute the Hessian, and the eigenvector of the Hessian will tell you the direction in which the system will distort easier. But if you didn't understand that sentence that I just said, basically the only thing that you need to keep in mind is saying that I have to distort I have to take the atoms in the direction where the system will distort easier. Therefore, I'm going to show you how that works. Let me think that this blue curve corresponds to the energy surface. Therefore, first of all, I will define an initial configuration that I created completely random. Therefore, what I'm going to do, first of all, is to go into the local minima. There are many different algorithms that allows you always to go into the local minima. The only thing that you have to do, for example, is to compute the gradient of the atomic positions and the cell parameters with respect to the, I'm sorry, the gradient of the energy with respect to the atomic positions and the cell parameters. And then you will be able, by following the direction of the derivative, go into the minima. This will be one of the simplest algorithms. Therefore, that's exactly what we do. You go into the to the local minimum. Now, what we do is that we find the direction in which the system will distort easier. And then what we do is just kick it out. Therefore, we apply a lot of energy in that direction. Therefore, we find the direction and we just kick it out very, very hard. And that will allow you to jump. That will allow you to jump to a different minimum. Okay. Therefore, what we do is we repeat the process. Therefore, we go into the local minimum, we do it. And if we do it enough time, this is the type of a structure that you get. And these three structures that you see on the bottom of the screen, they correspond to silicon carbide, and they correspond to the actual minimal crystal structure detected experimentally. Okay? For this method, if it is performed well and with care, you will be able to detect the low energy configurations. This is just to show you a very hard problem, which happens to be one of the most difficult problems to do, which is, let's consider that I have a piece of graphene, and I'm going to heat this graphene in order to get a buckyball. This is one of the most difficult problems from the theoretical side, because it happens that if you do it normally, you will find a buckyball full of defects. Therefore, it will not be the beautiful buckyball that we know. By using this method, we can show very, very easy that you will be able to find it with the corresponding number of hexagons and pentagons that correspond perfectly to the buckyball that we know of. Okay, and this is the corresponding the last method that I introduced, which is the comprehensive search. And what I'm going to show you is an application that we recently do by using this methodology and find all possible two-dimensional materials that you can create. Therefore, by following all the layer groups, I will be able to synthesize, theoretically speaking, all the possible materials that happens in 2 dimensions. Therefore, the process that we have is that the user defines the space group that is interested and defines the number of species, and just that. With the number of species, we go into the periodic table and take all the elements and create all possible combinations based on the number of species. Therefore, you can say, I want to find all binaries. That means that I go into the periodic table and create all possible binaries that I can have from the periodic table. I also need to define the system dimensionality, because that will define the space group. In this particular case, I will be defining the 2-dimensional case. Then I will go and check in the crystallographic books, which are going to be the corresponding positions for that specific space group. This is what we call the Wickoff positions. Sorry, they are very well known, therefore I don't need to compute it or anything. We know them perfectly. Therefore, based on that, now we have the Wickoff positions. Now the only thing that we need to do is a lot of combinatorics. Therefore, we have to do which of the Wickoff positions I have and which species I'm going to be occupied by that. Before doing that, there is one thing that you have to keep in mind, which is the so-called oxidation states. The oxidation state are all the possible electronics occupations that the atoms could have when they are embedded in a material. And these oxidation states are very well known. They are tabulated. The only thing that we need to do is to use them. Therefore, based on the Wickoff position that we have selected, we create all possible atoms, all possible combinations. Thousands of materials came from this analysis. After that, we applied the criteria that we can combine different oxidation states, but at the end of the day, the crystal structure have to be neutral. And then we have a series of materials that I'm going to be considered. On that, after that, I have to apply different type of criteria to select the best materials. I'm not going to go through that because time is running out, but I think we know perfectly what to do. And after that, we can create a series of material. And over here, I'm summarizing in a table the number of possible materials that I'm be able to create. For example, for space group 17, we have around 3,000 materials. And from those, 220 are chemically stable, which are 0.25 with respect to the convex fluid. This is, we compare, for example, the database that we have created with the one that is the most accurate one that exists, that was created by a group in Denmark. And the number of structures that they have reported is around 4,000 structures. The one that we have is around 7,000 structures. Therefore, we have 3,000 structures that are not reported in the literature and which are completely new. And we can now see and study the pattern. For example, this is few of the things that we can extract. For example, we can study from the two-dimensional material that we have created. We can study, for example, if we observe different tessellations. Tessellations are that you take a basic plane and you divide it in tilings, which are geometrical shapes that you can repeat ad infinitum to cover the two-dimensional space. And this is a representation that we get different tessellations, which are very well known. I mean, you have seen it maybe in on your curtains or something like that. Therefore, they are very well known. Therefore, what we are saying here is that in the case of atomic structure, we get also those tessellations. We are able to recover structures. We cover the two-dimensional space by using different geometrical shapes. The other thing that we keep in mind is, for example, we can see polyformes. That means that in the binary, for example, in this particular case, the copper iodine, we can see that by a small difference in energies, we can see a very large number of different crystal structures in 2 dimensions that you can get. And you can see that if you go from 0 up to 10 milli-electron volts per atom, 20 milli-electron volts, you see that the number of structures change, the coordination change, the shapes changes, and so on. Therefore, this, for example, represents the fact that you can exchange many different crystal structures, but by using the same chemical composition. And this is how we obtain the distribution of the different crystal structures. As I have, and if you want to have access to the full database is available to you guys. And if you go to this data, to this site, tddft.org, you will have access to play with it. And what you are going to see, for example, is that you can select the atoms, and then you can see the structure, you can see the energy, you can see the composition, you can see the magnetization, and you can see properties that we are now in the process of computing. It still is incomplete, but is going on the right momentum. Okay, this is one. And before we move, I want to show you another application that we have recently done. And after that, I think I can stop and take questions from you guys. Now that we have these two-dimensional materials, the next question that could come out, well, what we can do with them? Well, one thing that we can do, which is very interesting, is that we can look into a specific properties that these materials could have. In this transparency, I'm focusing in the case that we can find magnetism in these two-dimensional materials. And over here, we created a method that by taking the crystal structure that we found, we are able to detect the most important magnetic parameters. For example, in the B side of this plot, you will see, for example, some of them, how they look like. But what matters to me is that you notice the two plots that are on the bottom. The left-hand side corresponds to the so-called magnon spectra. The dots correspond to the experimental measure magnon spectra, and the line corresponds to the theoretical one. This corresponds to nickel oxide, a very well-known antiferromagnet. And you can see that we recover not only the magnon spectra, but we also can see where the magnetic moments are pointing out and what are the most important interactions. The other quantity that we can also compute is, for example, how the magnetization changes as a function of temperature. And we can define the so-called transition temperature, the Curie temperature. And what is important about that is that if you are going to use a magnet, what you care is not only if the magnet happens to be strong, but also what you would like to see is what is the temperature regime where you can use that magnet. That's very, very important. And in the case of two-dimensional materials, it happens that most of the magnets that people have been able to synthesize up to now, they do not have a temperature higher than 300 K. Okay, but now let me show you in my next plot, which is going to be the last plot. I'm going to show you the critical temperature of many different ferromagnets and antiferromagnets, and you will see that the line corresponds to 300 K, and we have detected a very large number of materials which have a Curie temperature which is larger than 300. We even have materials that we have around 1000 Curie, Kelvin. And I think if you think about that, means is that if I take a magnet with that Curie temperature, I can even put it into a rocket and put it in close to the combustion, and still the magnet is going to work, because the temperature it can resist without changing the magnetic phase, it will be around 1200 K. Therefore, that means that we are now in the possibility of designing new magnets that will be useful for different technologies, but it will have a larger stability. I didn't have the chance to show you many other applications that we have done in this field, but I hope I conveyed the idea of saying that even though from the theoretical side, we have created a lot of methodologies that are able to design materials without the support of the experiment, we will be unable to check that the theories that we have developed are really accurate enough. The other thing that is important to us is saying that due to that and due to the development that we have done theoretically in the last few years, we are able to create materials for a large number of new applications. And for example, you are going to see recently in the new technologies, things that are happening in the side of quantum computing, or things that are happening in the new developments of quantum devices, or things that are happening in the case of new electronic devices or optical devices. All of them that requires that we go to the atomistic scale require that we need to design those materials with a lot of care, which means that now we need to rely a lot on a joint effort between theory and experiment. And I think I prefer to stop here and take questions instead of giving you more examples, because otherwise you will not stick with me for more than 20 more minutes.
All right. Well, thank you, Professor Romero. That was an interesting talk. Right now, I will go ahead and open up the Q&A for anyone interested. Real fast, I do have a question for you here. I remember at the very beginning, you were talking about like separate methods with quantum mechanics, classical mechanics for the combination of certain elements. You showed that big cube and you had the 4 elements. Which one of those methods works the best for calculating that? Or is there a specific one that works the best, or do they all kind of combine together?
At the end of the day, it's a matter of what we call transferability.
Okay.
The thing is that when you design a classical potential or you define a tie binding potential, what happens is that you define it under specific conditions of binding. Therefore, you can say, I define, for example, a classical potential for carbon that is able to describe only sp and sp2 and type of bonding. Therefore, it's unable to explain, for example, what happened with sp3. If the material that you are trying to explain, it happens that it will have an sp3, it will not work. Therefore, at the end of the best method is what we call an ab initio method, something that doesn't require any input from the user. But the problem with those methods is that they are really, really expensive. Therefore, now people is starting to look into machine learning potentials, which if you are training them well, they can get with very good accuracy. But the problem with the transferability needs to be clearly evaluated. And I don't think that people have done it with a lot of care. People have tested that for the geometry that they have considered there is a very good accuracy, but it will be very interesting to see what happens if you consider structures which are very, very bad in energy, and if the machine learning potential will be able also to predict that as a structure that is also very bad. People have not done that very carefully.
All right. I got another one too for you real fast. I wrote down some just to make sure
go ahead.
that during the talk. What are some of the methods that you can use to calculate error from machine learning? Because you said that could be a big issue if those go kind of unnoticed. Is there a way
This
to
is a very
calculate that for
interesting
sure?
question. This is a very interesting question. First of all, there are methods which are in the arena what is called uncertainty quantification, which happens in the following way. In the case of DFT or any of the method that I presented, in principle, in paper, we have an accuracy of what the computer can give you. But there is also an explicit error that we don't talk about too much, is that we have done a lot of approximations into the theory. Therefore, we need to capture those errors some way. If you use only the theoretical method that you use, like for example, you use DFT under certain conditions and you train a machine learning based on that, then you will be able only to predict the energies based on those conditions. But that will not tell you anything about the actual error if you compare with the experiment. Therefore, now you need to come up with a method that is able to capture that. Uncertainty quantification, there are different methods that you can explore in which you can see, for example, the sensibility of the prediction of the parameters that you have to see what is the response that you get. You can also introduce the errors that you can compare some of the structure with respect to experiment, and then propagate those errors into the network and learn from the errors that you take from the experiment in the accurate calculation, and see how the machine learner will be able to compare with those.
Okay. Interesting. All right, so I got about 2 questions here on my phone that from friends of mine that are watching that didn't want to type into the chat. So let me pull up the chat real fast and let me go ahead and ask it. It's a friend of mine from engineering at Marshall here, and you mentioned about not being aware of an error is an issue. Would you be able to combine the different methods to get a higher success rate? Is that possible?
Oh, that's also a very interesting question. People is doing that, and we use what we call transfer learning in the case of machine learning. And what you can do is to train a neural network based on a particular property with a lot of structures. And then what you do is that you take the neural network and transfer that to a different application. And instead of training the whole network, what you do is that you froze some of the parameters that you train just a piece, which means that then you will need also a reduced number of configuration to train again the whole problem. The other method that you can use is what is called active learning. And that method, what it does is that it says, okay, you have used it and you have produced very good results. But what active learner is going to help is to detect the region where there is only very few data. Therefore, if you are able to detect those regions, then you can reduce the error, because now you can try to find new configurations in the region where the errors are larger.
Awesome. All right. I have another friend too who said he is pasting his question in right this moment. He just texted me and let me know.
Okay, we are patient. We wait for you.
Yeah, we can wait a little bit. So I told him, go ahead. So, Dr. McBride, do you have anything you'd like to say or ask?
So one of the things that I was thinking about was like just if properties to predict out. I was thinking about the magnetics, and as soon as I was thinking about that, you were showing it on the next slide. And I also did have an engineering student that was interested in the talk, and I sent him the link, and he hasn't asked a question yet, but in case he's not out there to ask it or doesn't want to ask it, I'll ask it for him. Is it possible then a lot of the properties that you're talking about are based on the sort of structure of the material on the atomic level, but can you extract out then predictions about like the mechanical strength of some of the materials based on the atomic structure and ordering of the crystal lattice that comes out then?
Right, that's a very interesting question, because from the physical side, we know that many of the macroscopic properties depends on the atomistic properties. Let's take one example. We know the thermal properties. We can compute the heat capacity. We can compute the thermal expansion. We can compute any one of those properties microscopically. Can we relate those properties to the atomistic? And the answer is yes. How do we do that? Well, the simple question is to say that everything that happens at the thermal response of a system happens because the ions are vibrating. Therefore, what we can do is to compute what are going to be the changes in energy due to the vibration that you have within the material. And that's what we call phonons. Phonons are the ones that capture the vibrations of the lattice. And then if you are able to compute the phonons, you can correlate the phonons into macroscopic quantities, like, for example, the thermal expansion, which is a macroscopic quantity. Therefore, you can do it. There are properties that are very hard to correlate, but people have developed techniques that by using approximative method, you can able even to predict them from the atomistic side. I think the most difficult part that we need to take into account is the fact that if you happen to have a system that have many different configurations, therefore you have what is called a polycrystalline sample, then at that point, we are kind of stuck because everything that I show you is a beautiful and perfect crystal. But then in experiment, that doesn't happen. In experiment, what happens is that you can have many different type of crystal orientations, and then you have to go back and then you have to study all the different configurations and then see how these configurations will change the elastic properties or will change the thermal properties and try to take an average of that some way. But it's doable.
Thanks.
All right. I got my friend asked the question in the YouTube live, so I'm going to go to it real fast. Josh Banzon, he is a computer information technology major at Marshall University. He has just the question, how did you know physics is what you wanted to study? And can you talk a little bit about some of your beginnings and anything you had, any maybe issues you might have faced or anything of that, nature?
When I finished my high school, I was not thinking about anything. Mm-hmm. Therefore, I decided, everybody's studying computer science. I should study computer science because that's the career of the future. Then but I was living in a very tiny city. Therefore, my brother went to the university where I was planning to study, and he went to register me into the computer science career. But the line for registration was very long. They said, no, I don't have time. Therefore, he decided to register me into civil engineering. Therefore, I started studying civil engineering for several years. Even I finished it up. I have a degree in civil engineering. But then when I was studying at the university, I just sat down in a physics class. And at that point, it was like a cold. Sounds kind of fishy, but no, it was really like a cold. I felt that was very interesting. I was very cool. And I started taking classes in physics, even though I was doing engineering. And at some point I say, this is my passion. And I decided to start doing physics most of the time. And then I finished my degree in engineering and in physics. And at that point I say, I don't know what to do with my life. Therefore, I received an offer to start my PhD in Germany doing physics. And I was in a very small, tiny town where everybody in the place was just speaking German, no English whatsoever. I was not, I didn't have a way to communicate with anybody. And I was got very bored. Therefore, I decided to come to the US and say, I'm going to find a place to study something. I mean, whoever is able to pay me, I will go there. And therefore, this guy that was in hydrology invited me to work on chaos theory. Therefore, I developed my computational effort doing a lot of chaos theory. But then when I was there, I met a lady that was looking for a graduate student at UCSD, at the University of California, San Diego, and say, if you come and study chemistry, I will pay you. And I say, well, you pay me, I will go. No consideration, I will go. Therefore, I went to San Diego and started to do my PhD in chemistry. And it happens exactly the same thing when I was doing my degree, my undergraduate degree. My call in physics still knocked my door, and then I decided to study both of them. Therefore, I finished a PhD in physics and in chemistry because of that. Therefore, it was never like a straight line passion. No, I was hitting several walls until I found my way. And I think that happens usually. You don't have an actual solution for a problem. You have to sometimes you have to try several things. You have to find whatever moves you, something that you really get excited about it. And at that point, you will say, that will change my life. As soon as you find something like that, that's it. You are done. Just focus and enjoy it.
That's a fantastic story. What town, by the way, in Germany were you at? What's Max Planck?
I was in Jülich originally when I was doing my PhD. And Jülich, it was a nuclear reactor of the old times. During the 60s, it was a nuclear reactor, but after that was converted to a research institution. And I was living in Jülich, which have maybe a population of 5,000 people. maybe 90% are only farmers. And there was only a movie theater that opens on Mondays to give a German movie. That was crazy to me. I was completely unable even to go to the movies.
That's awesome to hear about. Yeah. And then that's sometimes how it seems to work out. You're not looking into something, and then it's just that seems like you're calling. You sit in that one class or talk to that one person, and then it just makes sense to go in that direction, even though it wasn't the direction you started with.
I can tell you even more. I think you that now are undergraduate, many of you that are listen to me are undergraduate. You can think like the following: if you are an undergraduate and you know what you are doing in life, that's fine. That's fine. You can fall several times, but at the end of the day, you are in the best time of your life, because if you know what you want to do, maybe you solve the problem. But if you don't know, try everything, but open your mind and go and talk to people in physics, talk to people in chemistry, and learn a little bit about them. Go and talk to faculty and enjoy talking to them by speaking about any topic that you want to discuss. And at that point, you will realize maybe that you want to pursue a specific topic, but don't get afraid of things. I mean, I think the point is that we have skills, but I think the most important skills is being perseverant, is work a lot. You don't have to be too smart to do that. You just need to be very hardworking, and you will make it to the other side for sure.
So you're always in search of your global minimum, hopping around from one to the
other. Probably I will not find it ever, but I will try all my
best. That's right. There you go.
I mean, sometimes you need a beer for energy, that's for sure.
All right. Well, that concludes, I guess, our Q&A session. And thank you again for the very informative talk, Professor Romero. That was awesome. Dr. McBride, do you have any words that you would like to say before the end?
Just again, thank you for your time, and that was a really good talk. And these will be video links that will be available on our YouTube channel. So that, again, viewers that might not have gotten a chance to see it, they can always go back and watch it later. That is honestly when a lot of our videos pick up a lot of their views is post talk. So share the link with your friends. And again, if you're interested in what you heard tonight, please contact Dr. Romero. And if you're interested in SPS and things like that here at Marshall, just shoot me an email and I'll be happy to talk to you. And same about a physics degree program. Look at your options and shoot us an email if you're interested in studying physics like Dr. Romero was and still is. Please shoot us an email and we'll be happy to point you in the right direction.
All right. Well, thank you again, Professor Romero, for your time.
Thank you. Thank you for the invitation. I really appreciate it.
We enjoyed having you here for our talks, and everyone in the live stream and who might be viewing this later on. Stay tuned for more Faces of Physics speaker series. We will be having hopefully some more later this month or later this spring semester. So with that, I guess that will conclude it. I will see you all when I see you all. Thanks again for watching. Bye-bye.
Bye, guys. Thank you.
All right.
So that's the end of the live stream, right? So